Welcome to a special introduction to exploratory factor analysis in R in what I consider an applied manner that you would see in a real world setting. During the first demo, you're going to learn how to perform a unidimensional exploratory factor analysis on examinees' responses to a set of questions called items. We'll then analyze two key outputs of the EFA. The factor loadings of the items are going to measure their association with the underlying factor, and that's going to indicate their performance. The factor scores of individuals will estimate the level of the underlying factor they possess, and that's going to be helpful in scoring the examinees. You might already be familiar with some similar approaches to analyzing data. And factor analysis can be seen as a middle ground between classical test theory and structural equation modeling. While classical test theory calculates scores as the sum of item scores without any weighting, factor analysis assigns weights to items based on the correlation matrix. And these correlations allow us to infer the existence of an underlying variable or variables. Structural equation modeling takes this approach further by modeling the relationships between these latent variables. Factor analysis can be categorized to two types, exploratory and confirmatory. Exploratory factor analysis aids in the creation of measurement tools by exploring the factor structure and then identifying which items accurately measure the construct. Conversely, confirmatory factor analysis is utilized to confirm the validity of the measurement tool once it's already been developed. In this demo, we're going to primarily use the Psych package developed by William Ravel. You can load this package using the library function. To use this demo effectively, it's important to understand that the main tool being used is the Psych package. And this package is created by somebody who's considered an expert in this field, which is going to enable you to make the most of the features provided in the Psych package. In the first demo, you'll utilize the GCBS dataset. And this particular dataset comprises 2,495 responses to 15 multiple choice questions. These questions, or items, have been designed to assess the extent of belief in conspiracies among respondents. The GCBS dataset classifies items into 5 distinct conspiracy facets. To illustrate, item 2, which states the government allows or carries out acts of terrorism on its own territory while disguising its involvement, falls under the category of government malfeasance. Similarly, item 8, which claims that evidence of alien contact is being hidden from the public, belongs to the extraterrestrial cover-up facet. The content suggests that the 15 items are believed to represent 5 different categories. These categories are thought to be connected to 5 underlying factors. These 5 factors are associated with a higher order factor known as conspiracist belief. In order to evaluate this hierarchical structure, structural equation modeling is required. However, exploratory and confirmatory factor analysis can also be used to examine either a single factor or a 5-factor structure. And in this initial demo, you're going to disregard the 5 lesser important factors and utilize a single factor exploratory factor analysis to assess the relationship of the items to conspiracist belief. And in this analysis, this is to provide you with insights into how effectively each item measures a single underlying factor, as well as information on the extent to which individuals possess this factor. Techniques for dealing with multiple factors are going to be covered later. And by following this approach, you can focus on understanding how each item is related to the main factor of interest. And then you're going to gain clarity on its measurement and the extent to which individuals exhibit the factor. The FA function is a powerful tool in the Psych package that allows you to run exploratory factor analysis. And when you use this function, it creates an object that contains a wealth of valuable information, including factor loadings for items, factor scores for individuals, and fit statistics. In this first lesson of the demo, you're going to learn how to use the FA function to run a single factor EFA, explore and interpret its output, and visualize the results. Now that we've discussed the fundamental theory behind factor analysis, I want to dive into some actual code and put the knowledge into practice. So, to start out with unidimensional EFA, I want to begin by using the Psych package and conducting a single factor explanatory factor analysis. And here we're going to use the FA function, which conducts an EFA on your data. And when you're using this in the real world, be sure to use a data set that only contains item responses. Other types of data will cause errors and or incorrect results. In the GCBS dataset, these are examinees' responses to 15 items from the generic conspiracist belief scale, which is designed to measure conspiracist beliefs. An EFA is going to provide information on each item's relationship to a single factor hypothesized to be represented by each of the items. EFA results give you the basic information about how well items relate to that hypothesized construct. Be sure to save your analysis results in an object so we can return to it later. And I will now go through a demo of how this is going to work. So I will have the GCBS data for you. And once you download it in your downloads folder, this is where I like to keep it. If you have a particular file source location, please use that. For me, I'm going to use my downloads. And this is an RDS file. So you've worked with CSV files, you've worked with Excel files. You probably have not been exposed to .rds files just yet. That stands for an R dataset file. So in other words, when you open it through RStudio, it's going to automatically open in your environment. And I'll show you. So I go to open an existing file. I go to, it's in my downloads. This will be the file name that you'll have. And it says load R object. Here, I'm just going to call it GCBS. Try to use lowercase when you are naming your object for the data. It's easier to call on, it's less prone to error, and it's just standard programming practice. So what this is going to do, because it's an RDS file, it's going to automatically load the GCBS dataset into my environment, which is right here. Once I press OK, boom, this right here, I like to take, so I can put it in my source code for later. And I like to always comment using the hash symbol. This is the best practice so that you actually understand what you are doing in every single line of code. Always comment. And here I'm going to say load in the GCBS data set. You also want to comment in a manner that speaks to all audiences. In other words, someone who's a brand new programmer to R should be able to look at your document and understand exactly what is going on. So the first thing we're going to do is load the psych package to gain access to the necessary functions for the EFA. So once again, I'm going to comment so that anybody who has minimal experience with R or none knows exactly what I'm doing. And this is going to make you better at R. You're going to master it faster than you ever thought you could. If you're one of those individuals whose anxiety surrounding R is high, that's okay. It's a steep learning curve. That being said, you need to really focus on all the different tips and tricks you can take in to be successful in using R. And one of the things I can't recommend enough is comment your code. Now we're going to load the psych package, and I'm going to do that by running a library statement, open the parentheses, and type in psych. For those of you who are true beginners, you'll know that you also need to install this first if you have not already done so. So I can put install the psych package. I already have it installed, but it's okay to run this. So I'm going to just type in install.packages, and then I'm going to put psych, highlight that, and put double quotes around it. Automatically pulls that in. It says updating loaded packages. So therefore, we're going to restart R. Awesome. Don't worry about these errors that I'm getting. Something's going on in my environment that I will take care of on the side. This restarted my R session. Here, I successfully installed the package psych. You always need to do updates to your packages too. So that's why this will not hurt. It'll make sure it's completely updated. Now, you cannot just run the psych package. You have to load it. Now we load it. Cool. We're now going to conduct a single factor exploratory factor analysis on the GCBS dataset. Then we're going to save the result to an object in our R environment named EFA underscore model, because we're going to need to call on this object later so that we can actually see our results. So here we're going to name the object EFA underscore model. And what are we storing in this model? Well, we want to put something. Can we put calculations? Can we put a mean, right? Every time we do this, we're storing it so we can get the results later. So what is going to be an EFA underscore model? Well, this is going to be the results of the factor analysis on the GCBS data. When I run that, nothing happens except it shows in my console, meaning it's ran, but I cannot view the results yet. This means I need a call on the EFA underscore model object to see how the items in the dataset relate to the extracted factor. Now, before I do that, I want you to take a quick look at the EFA model data set first, and it's just a matrix of questions. If you have participant IDs here, this will not work. So when you're trying to run an exploratory factor analysis, you're going to clean your data first. Then once it's in this format with only the questions you want to analyze, you can proceed with these analyses. Always comment, and I'm gonna put that conduct a single factor EFA. Now I want to view my results. This may seem repetitive, but trust me when I say you're going to become a better programmer because of it. You can just write EFA underscore model and run that. Best practice, if you want to really maximize your potential as a programmer, simply take the extra step and put print the EFA model. Again, it's just one of those things that it's kind of standard practice and it'll help you out in terms of navigating the platform. Now, I also see that students highlight a lot and press run, and doing that back and forth can be a little time consuming depending on the length of your code. So if you're an Apple user, you can just press command return. If you are a Windows user, you can just press control enter. And here's that. And it does the same exact thing as if I were to highlight this and run it. So now that we know how to conduct a single factor EFA, let's look at the results. This tells us the variable's relationship to the factor of interest. You can see in the results that the function has named the factor MR1. This name is due to it being the first factor extracted using what's called minimum residual estimation. And if we're looking at these loadings, all of the items load very high on this one factor. We also see our fit indices, which we'll talk about more. But from lecture, remember the principles of what we need to check our model to make sure that it's a reliable model and it's valid. And before I proceed, save your code. So let's just call this EFA analysis in R. And then I'll add a little note using Psych package, because there are other ways you can use EFA. So this is just an extra step to tell you how you did it. I'm just going to pop it in my downloads again, just because I'll come back to that later. You can place it in whichever source file you would like. So if we're viewing and visualizing the factor loadings, each factor analysis function result, so this right here, FA, each result object is actually a list, which is what you see here. And each element of the list contains specific information about the analysis, including the factor loading. So once again, come here, you can look for your loadings here. So there's a bunch of information about this model. As a reminder, factor loadings represent the strength and directionality of the relationship between each item and the underlying factor. And they can range from -1 to 1. You can also create a diagram of loadings. And we're going to use a function called fa.diagram that takes a result from the object of fa. In other words, here's our object from fa. Here's where we stored it as an object. And then we're going to use another function and call on this again so that we can actually get our factor loadings and create a path diagram showing the items as loadings ordered from strongest to weakest. And path diagrams are more common for structural equation modeling than for factor analysis, but this type of visualization can be a very helpful way to represent your results. So the first thing we're going to do is we're going to view all the factor loadings. So I'm going to state that. View the factor loadings. Well, we have an object stored, and recall what the $ is in R. So for my new users, the $ is used in R to call on something from an object. In other words, remember how I had this list and there's a bunch of different elements in this list? Well, what if I want to look at one element or two of them? Well, every time I want to look for one of these elements, I need to first call on the object, then use the $ followed by one of these names in terms of which element do I want to look at. For me, I want to look at the factor loadings. So again, to view the factor loadings, we're going to put EFA underscore model, because that's what we called it, $, and notice all the options pop up for me in RStudio. That's what's beautiful about using this. I'm going to look for the factors loadings. Ooh, I see loadings here. And again, this is me guessing, but it's pretty intuitive. I'm going to take a guess and say that this is correct. And you can run it here or command enter or control enter, and it runs. And I'm given all of my factor loadings now. Notice they're very high, all above that threshold of 0.3 for acceptable and 0.5 for very strong. Therefore, this is looking good for the one factor model. But I want to create a path diagram of the items as factor loadings themselves. And to do that, I'm going to use the fa.diagram function. Remember, this function is part of the psych package. As an aside, one cool thing about R to help you start memorizing packages that I've found helpful is you can call on the package first, psych, do a double colon, and then you get to see all the functions within that package. And then you get like a description over here. I really like this feature and I use it all the time. You can also use it so that you actually don't have to load the package to begin with, but keep in mind that means you have to call on this package using the double colon every single time. So here I'm going to look for the fa.diagram, which is right here. Boom. And notice the first argument, fa.results. Well, think about, where did I put those results? I put them here in the EFA model. So before I do that, for good practice, type in create a path diagram of the items is factor loadings. Now I need to put something in here. I'll just take my EFA model. So Command C, Control C if you're Windows, Command V. So let's visualize the results of this diagram. Command return, Control Enter, boom. Check out our plot. Now we can view the factor loadings as a matrix, which we did here, or visualize as a path diagram. And this is really good practice in terms of how do I relay information to less technical audiences. Data visualization is the way to go, because you may know what this matrix means, but somebody who's just not familiar with these types of models, it's easier to explain visually. Notice that they're in descending order, not in the order of the items. They're in descending order of strength. And this is one factor, the MR factor that we were talking about earlier. Now, to interpret individuals' factor scores, the EFA underscore model object here also contains a named list element scores. So if I go here, I can see our scores, R squared scores. So I'm going to call on this one scores. These factor scores are an indication of how much or how little the factor each person is thought to possess. Factor scores are not computed for examinees with missing data though. So the first thing we're going to do is we're going to take a look at the first few lines of the response data and their corresponding sum scores. Well, great practice, comment everything. We can do this using the head function. By default, it's going to print the first 6. You can set this to anything you want though. So I'm going to go head. And by the way, why would you use this? Well, we don't want to print out all 2,495 observations. We just want to get a quick scan. So I'm going to put GCBS. This is from the data. Run that. Great. We get to see what our matrix looks like. Now, again, let's say I wanted to look at the first 10 though. Just add a comma and put n equals 10. You get the first 10. If I want to look at just the first 3, if I want to look at the first 70, well, it maxes out at 66, folks. So there you go. Fun fact, you can also look at the last rows. You can look at tail and you could put GCBS and you'll get to see the last observations in your data set. And I'll just actually comment that. Take a look at the last few lines of response data and the corresponding sum scores. Okay, now we're gonna use a new function. It's called row sums. And if you think about it, it's in the name. There are a bunch of rows. And it's row sums, meaning in this row, I'm going to sum across. And then it'll do the same thing for every individual in the data set, meaning we'll get a final score here at some point. So let's take some row sums. So if I want to look at the row sums for the first 6 respondents, I'm just going to nest the function. So I'm going to type in row sum, and then I'm just going to do the first couple observations. Place that in there. If you did not do this, it's going to try to take the sum of every single row and try to print out the whole thing. And then you'll get this message, omitted a bunch of rows again. So I just want to look at the first. Fantastic. So if I'm going back to just this function, the head function, this means 5 plus 5, 10, 13, 18, 23, 28, 33, 36, 40, 45, 50, 55, 58, 63, 68. That is how we got this first value. Each other value is the subsequent row beneath. Notice a bunch of 1s, 15 questions, 15 points because it's a row sum. In other words, when you're looking at this, These values are going to tell you how much of the construct they possess. Next on the agenda, we're going to use the head function again to look at the first few lines of the response data and their sum scores. And comparing these is going to help illustrate the relationship between responses and factor scores. So now we are going to look at the first few lines of individuals' factor scores. We're going to do that by using the head function again. We're going to nest. Well, if you remember, the factor scores are stored in our EFA model. And then we're going to call on an element from the object. Recall, we need the $ followed by, well, we need factor scores. So let's find it. Scores. And I'll run that. Boom. And then I want to get a feel for how the factor scores are distributed. I want to look at their summary statistics and a density plot. To do this, comment, get a feel for, we're going to get a feel for how the factor scores are distributed and look at summary stats and a density plot. Well, how do I do that? We're going to use the summary function. And once again, we're going to call on the object where our factor scores are located. So they're stored in the EFA model. To call on the element, $, and just type in scores again. Let's get a summary. Okay, I'm looking at the distribution. Max is 1.94, negative 1.85 is the min. Okay, that's good news. Our first and third quartiles are relatively similar in terms of absolute value. Mean, median are close to 0. Okay, this is good. If I'm giving a quick look, I'm liking what I'm seeing, but I also want to see a density plot to really get a visualization for not only myself, but non-technical audiences. So to do this, we are going to use the plot function and the density function. And this is to create a density plot of the estimated factor scores for a visual representation. And then density plots show the distribution of data over a continuous interval. And this will give you a sense of what your data looks like. So I don't need to comment because I put a comment here. I'll keep it in the same line. In fact, let's separate it out. Let's put density plot. That would be best practice. So this is where you're going to need to nest functions again. So bear with me. You could do this two ways. If you're a beginner, maybe we can go from the inside out. And if you're more advanced, we can start from the outside in. So from the beginner level, to get a density plot, we use the density function. Well, what do we want a density plot of? Well, we want it from our EFA model of the scores. So I'm just calling on the same thing. However, density plots do not show missing values. We're working with computers and you have to think in terms of how the computer thinks. It's going to give you an error if you just run this. So what we are going to do is we're going to remove our NAs from the data set. Now, this doesn't mean that you always have NAs, in other words, missing values, but it's most likely the case in a real world setting. So NA.RM, one equal sign equals true, all uppercase. This is important because I'm saying remove the NAs and it's logical. Do I want it removed? Yes, this is true. If I don't want you to remove it, I would put false. Capitalization matters, so keep that in mind. This needs to be uppercase. Now, if I run this, all right, it's going to give me a list of scores for X and Y, a bandwidth, but it's not giving me a plot. And that's because I now need the plot function. But what do I want to take a plot of? Well, I want to take a plot of the work we did here. So that's what I meant by going from the inside out. Now we'll put plot and open the parenthesis because we're going to do a function within a function. This means you need a comma because we want a plot of this, but we also have to give other arguments, such as, well, what am I taking a plot of? You got to tell your audience. And this means we're going to use the argument main. Main is standard in R for the main title of your plot. And it even shows you right there. So we're going to put main equals, double quotes, factor scores. Now, if I run this as is, I'm going to get an error. And you should see that with this X. There's an unmatched opening bracket. So I'm going to close that. And when I run it, we're going to get the visualization here. Boom. It gives us our total sample size, bandwidth, our factor scores title. It shows you the distribution from here. Look at the Y's, look at the X's. So we get an idea of what our data looks like, which is great because it's looking like it's normally distributed. For the more advanced users who did not need to do it this way, what you could do, if you know how functions within functions work, we can just go from the outside in. So we can say plot, we want to plot an X and a Y. Well, those are going to come from our score. So we don't actually need to give it two parameters now, which is great. What do we want to plot? We want to plot our density function. And what are we taking the density of? We're taking the density of EFA underscore model object and the scores that live in there. But we know we'll get into an error if we have missing data. So the comma and remove those NAs. In other words, remove those missing values from the analysis ahead of time by saying that. Okay, we're missing our title. So you need to remember that where it's nested ends. So we have the density function that ends here. So this means we're still in the plot. Notice where it's highlighted. If I put that here, it highlights here. So it tells me what am I working in. So if I'm outside here, put a comma, and again, I'm put main equals factor scores. Either approach works. I just want you to be well versed on different ways to look at programming. So now that you've learned how to perform a single factor EFA, you're now prepared to consider how it fits into the overall process of developing a measurement tool. Take this knowledge and use it to move forward in your measurement development journey. Now, when you're developing a way to measure a variable or variables that cannot be directly observed, it's important to follow a specific process. And in this case, steps 1, 2, and 4 are more theoretical in nature and do not involve any coding. So we're not going to dedicate all the time in the world to these ones. So when you're determining the construct you want to measure, the first step is to create questions or items for your measure. And it's important to write more items than you think you'll need, as not all of them are going to perform as well as you hope. Once you've developed enough items, the next step is to gather pilot data from a representative sample in order to test the measure. These data will be used to evaluate the function of your measure before using it for real. You can consider the GCBS dataset as pilot data for these 15 items. And once you have pilot data, the first thing to do is examine what the dataset looks like. So we're going to use the describe function to gain an understanding of the data. And this function provides basic information about each item in the dataset. By examining the first row of the output, you can observe important details in the N column for item Q1. It shows that there's 2,495 responses with a mean of 3.47 and a standard deviation of 1.46. The minimum and maximum values of 0 and 5 respectively indicate that these items have been scored on a Likert scale. Analyzing this data will give you a clear picture of the data set. And now that you have a better understanding of the key features of your data set, it's time to consider the specific analyses you want to perform. If your goal is to develop and validate a theory on how different items are connected to underlying factors, you'll need to utilize both EFA and CFA on your data set. In this case, you'll also have to divide the data set into separate parts, which is described into step 5 here. To accomplish this, you can generate a set of random indices and utilize them to divide the dataset. Initially, determine the total number of rows in the dataset and create a sequence ranging from 1 to n. Then, make use of the sample function to randomly select half of these numbers and assign them to the indices underscore EFA object. The remaining half of the sequence numbers will be assigned to the indices underscore CFA object. With these established sets of indices, you can create 2 separate data sets, one for the EFA and another for the CFA. By constructing a hypothesis using half of the data and subsequently testing it on the other half, you can prevent the occurrence of overfitting your model or mistakenly validating your theory. Now, to summarize, the process involves generating random indices to divide the data set into 2 parts. One part is used for developing a hypothesis, while the other part is used for testing the hypothesis. And this approach helps in avoiding issues like overfitting and erroneously confirming the theory. After dividing your sample into 2 random halves, it's important to ensure that these halves are similar. This is the 6th step in the process. If the halves are not similar, they do not accurately represent the population and should not be used to evaluate your measure. The Psych package offers convenient functions for examining a dataset based on a specific grouping variable. And to achieve this, you're going to create a grouping variable using the indices that you generated to divide the data. The GCBS dataset can be enriched with a new column by binding the grouping variable using what's called the cbind function. And that stands for column bind. This grouping variable contains the necessary information for describe by and stats by functions to display important summary statistics. However, I want you to be cautious because while the group argument of describe by function must be a vector, the group argument of stats by in that function should be the name of a column in your data frame. And let's get started with the next demo. Okay, so now we're going to take some descriptive statistics of our data set. And the Psych package provides several functions to help us visualize the data. Specifically, The describe function tells you basic statistics about each variable in the data set, including the number of complete cases, which means how many non-missing cases, the mean, standard deviation, the minimum, the maximum, range, skewness, and kurtosis. You can also view graphical representations of the error bars for different variables using error dot dots, open the parentheses, which is a function. So error dot dots function and the error dot bars function. Both of these graphical representations are created from the summary statistics available from calling on describe. So the first thing we're going to do is make our notes. We're going to calculate basic descriptive statistics. And again, we're going to need the describe function. We're going to write describe, and we're going to put in the name of our data set, GCDS. When I run that, I get all 15 variables, which here are all 15 items, and we get the sample size for each. So these are all the complete cases, the mean, standard deviation, median, trimmed mean, the mean absolute deviation, the min, the max, range, skew, kurtosis, and standard error. And now I want to create a dot chart of the mean scores and confidence intervals for each variable in the data set. And I'm going to do that using error dot dots. This is from the site package. We're going to do a graphical representation of error, which means we're going to need the error dot dots function. And as a reminder, if you did not know what the name of the exact function is, you can just type in psych, double colons, and you can find it here where it says error dot dots. And that means here's our arguments that we need to put in. So I'm going to put error dot dots there. I'm going to put in the name of our data set, GCDS, and get a nice plot for confidence intervals around the mean. Lastly, I'm going to create a bar chart of the mean scores and confidence intervals for each variable in the data set. And this, I'll need error.bars, or alternatively, you could type in psych, error.bars. And now I'm going to put in the name of my data set, what I believe are called violin plots. So now we have a feel for our data set with basic descriptive stats and the visualizations of our error terms. Now we're going to go into the heavy lifting, which is splitting our data set. Now, during the measure development process, it's important to conduct EFA and CFA on separate data sets because using the same data set can lead to inflated model statistics. Instead, you can split your data set in half and then use one half for the EFA and the other half for the CFA. So first, we are going to establish two sets of indices to split the data set. And this is going to be done by determining which rows belong to each data set. And here we use a generic n, and that's going to be the number of rows. So n row is the function, and that just tells you the number of rows or columns of an array. In other words, I want to know what are the number of rows for GCBS. I'm going to hint that, get an n. There's 2,495, which is expected. Now I want to call in the indices. So here I'm going to store it as an object, my indices, and I'm going to take a sequence from 1, 2, and then this is where I need to split my data set in half. I'm going to need to take a sequence. So remember that each set of indices contains half of the total number of cases. The second set of indices is going to be defined as all row numbers not included in the first set of indices. And the first set of indices should be used to create the EFA dataset, and the second set should be used to create the CFA dataset. So here I'm going to have a sequence from 1 through n, which is 1 through 2495. I type that. Here are all my indices. Now I'm going to make my first dataset, which is going to be indices underscore EFA. And that's going to be taking a sample from our indices object. We're going to do what's called a floor statement. And this floor function returns the largest integer that's less than or equal to the number set as a parameter. So in other words, the floor function can be used to round down the numbers or to extract the integer part of a number. And it can also be used to find the greatest integer less than or equal to a value. And that means I want half of the total rows. So here we go, indices underscore EFA, boom. So now I need to make it for CFA. So we're going to call it indices underscore CFA. And here here, we're going to take it from the indices object. Then this is where we need to use what's called the subset brackets. So we're going to take a subset from indices, which makes sense. We want the other half of this object. In other words, we want what is not in this object, indices EFA. So it's like everything else. So we're going to start this with the exclamation, and the exclamation means not. So it is exactly the same thing as saying not, except that doesn't work in R. You need to use this symbol, and we're going to open this up. And within this function, we're going to say it's not anything from indices that is currently in the new thing we created, indices EFA. So let me kind of go over this. I'm saying take all the values from indices that are not in this vector. In other words, the other half of what we didn't take, and then store that as our CFA indices. I guess I should comment that too. So this is just taking the elements from indices that are not elements from indices that we initially put in indices EFA here, and then we store it as indices CFA. Now, this is splitting the data set, and we use splitting in our data set for what's called creating a training and test data sets. And this is for machine learning, as well as any other types of models as well. If you think of machine learning, think of AI. And now I'm going to use these indices to split the data set into halves for my EFA and my CFA code I made. So if we're looking at this, I'm saying in the GCBS data set, take the elements that are in indices underscore EFA. And notice it's indices underscore EFA and a comma and then a space. And that's because anytime you're using subsets, it's always a row by a column. So this is R by C. In other words, if this is blank, you're taking all the columns, but you're taking also the rows from indices EFA. And then you're doing the same thing here. In the GCBS dataset, give me the rows that we put into the CFA one, along with all the respective columns. And then we're restoring it. And here, look, we've now created two different data sets. We have a training data set and we have a testing data set. So let's compare the halves of our data set. So just like we inspected the features of the full data set, we need to examine the halves after we've split the data. And you can always use describe on each data set, but the psych package also provides some functions to compare a data set according to a grouping variable. Now, what we're going to do is we're going to use these indices that we just created when splitting the data set to create a grouping variable and then attach it to the GCBS data set. Once that grouping variable is set, you can use describe by and stats by to view basic descriptive statistics as well as between group statistics. And I want to give you a word of warning. While the group argument of describe by has to be a vector, the group argument of stats by has to be the name of a column in your data frame. Plan this accordingly. Let's start. So what we're going to do first, bring a comment in, we're going to use the indices from the previous exercise to create a grouping variable. And the way we're going to do that is we're going to say, here is a group variable, and it's going to be a vector, and it's going to be of the type numeric, and we need the number of rows from our original data set. We have group var right here, boom. Now what I want to do is create a dichotomous grouping variable from these indices, and then we're going to look at it. So here we need our group variable that we just created, but then we're going to subset, and we're going to subset it from the indices from the EFA data set. And we're going to say that is equal to 1. So we're creating a group variable where 1 are the indices from EFA and 2 are the indices from CFA. When we run that, we create our grouping variable. See here. Now we are going to bind this grouping variable onto the GCBS data set. And we need this so we can look at this from the overall data set. So we're going to combine columns. In other words, I'm going to put these indices in our GCBS data set. So here I'm creating a new variable called GCBS grouped using a column bind of all the columns from GCBS and our new column group var that contains these values. When I run that, we're good. It's new grouped. And notice now I have a grouping variable in that data set. You do not want to put this in the original data set because remember, when we're running a factor analysis, you can't have anything like this or you're going to get bad results. So we create a new object data set so that way we don't actually ruin the original structure. This is just for descriptive purposes. That's why. So now let us compare the stats across groups. And here we're going to use the describe by, and then we're going to use the stats by. I want to show you two different methods. With the describe by, now I get summary stats for that group var. But when you use stats by, you need to put this in quotes. And this helps you see correlations between and within groups. We're now going to go over measurement features, so correlations and reliability. By this point, you've looked at basic descriptive statistics of your data set and learned how to split the data into random halves. Now, when writing a description of your measure, you'll also want to include some more detailed information. When analyzing your data set, it's important to measure features such as correlations and reliability. After examining basic descriptive statistics and splitting the data into random halves, you should include more detailed information in your measure description. Correlations are commonly used to assess the relationships between variables. The lower core function provides correlation data in a more reader-friendly format compared to the core function in base R. The correlation matrix produced by lower core only displays the lower triangle, where each pair's correlation is shown once. This matrix can give you insights into the factor structure as items with stronger correlations tend to load onto the same factor. To determine the significance of correlations, p-values can be calculated using the core.test function. This function generates a full matrix of results, including p-values for each correlation. In this example, all the zeros indicate statistically significant correlations. However, it's important to note that statistical significance can be influenced by sample size. Furthermore, you can use the core.test function to obtain confidence intervals for each correlation. By default, it calculates 95% confidence intervals around the correlation value. These intervals provide important information for reporting in various publications. Coefficient alpha, which we all know as Cronbach's alpha, is an important statistic for assessing the internal consistency or reliability of our measurement. A coefficient alpha greater than 0.8 is generally preferred in the literature. The alpha function can be used to calculate Cronbach's alpha for the GCBS items. Here, the calculated coefficient of alpha is 0.93, and this indicates excellent reliability. In addition to Cronbach's alpha, the output from the alpha function also provides basic statistics for each item and shows how the overall alpha would be effective if an item were dropped. An increase in alpha when an item is dropped suggests that the item is not performing well. And lastly, split half reliability is another statistic that measures internal consistency and reflects how well two halves of the test relate to each other. The split half function provides various split half statistics, and it's common to report the average split half reliability. In this case, the average split half reliability is 0.93, which is, by the way, just coincidental to our Cronbach's alpha. Now it's time to put all these functions into practice and then apply them to the GCBS dataset. So the last part of this demo is to view and test correlations and look at our alphas. Now, one of the easiest ways to get a feel for your data set is to examine the relationships of your variables with each other. While base R has the core function, the psych package has the lower core function, which only displays the lower triangle of the correlation matrix. And you can also use the core.test function to view several probability values, including p-values from t-tests of each correlation and confidence intervals for the correlation. P-values are corrected using what's called the Holm correction by default. So the first thing we're going to do is we are going to view the lower triangle of the correlation matrix. And we're going to do that using the lower core function. We're going to do that on GCBS. And when we run this, the beautiful correlation matrix, all 15 observations. Now I want to check out the p-values that are created when calculating correlations. And I want you to remember, significant values mean items are meaningfully correlated. And I'm going to do that using the core.test test function. Notice there's two R's here because this is coming from the psych package. And if you need to remember that, remember, type in psych core and you'll come up right there. And we'll do this on GCBS. But remember, I want the p-values. So like any other object, we're going to use a $sign. And it's very simple. All you have to do is put p. When I run this, I get p-values. And here we can say which of these items are meaningfully correlated. Next, I want to view the confidence intervals when calculating correlations. So I'll put a note here. And once again, I'm going to use the core.test, but it's slightly different. Here, we're going to call in the GCBS dataset. We're going to add a comma and another argument. It's going to be the use equals, and then you have to use quotes. And we want pairwise complete observations. This means that they're only going to take the observations without missing data. When we close that parentheses, we're going to add a $sign and type CI. This is just going to give us the confidence intervals for these calculated correlations. When I run that, now I get my lower bound, my upper bound, my sample R, my p-value. So now that we can view variables as correlations as well as their p-values and confidence intervals for these correlations, let's look at internal reliability. You know how to examine how individual items perform in your measure, but what about how well those items relate to each other? That would be the overall internal reliability of a measure. We have, again, coefficient alpha, which is also known as Cronbach's alpha, and the split half reliability as the two common ways of assessing reliability. These statistics are a function of the measure length and the items' interrelatedness, which you just investigated by looking at the correlation matrix. In reliability, values that are greater than 0.8 are desired, though some fields of study have higher or lower guidelines. And what we want to know is, do the results of using the alpha function and the split half function indicate that the questions from GCBS have acceptable reliability? So let's start off by estimating the alpha coefficient. And we're just going to use the alpha function on GCBS. Okay, based on this, we get a raw alpha of 0.93, standardized alpha of 0.93. We meet the threshold. Now we're going to use the split half reliability method to also find out. So we're going to calculate the split half reliability, and that's just going to be done using the split half function on the GCBS matrix. When I run that, we're going to look at the average, which is 0.93, which is over than 0.8. So we are good. So we can conclude that the GCBS dataset has acceptable reliability because both indices are above 0.8.